Okay, so here's another video. This is the same example that we did a little while ago, or in the previous video, example 4.4, but it's just using English units, or we should say American units, because I don't believe that the British are clinging to our BTUs and whatnot. This is an important one because there's lots of material that exists in the world that you will want to use, engineering resources you'll want to use that are still in this system of units. So you want to be comfortable with it and know about the pitfalls that might take place. So we have about pretty much the same thing. We're using steam, but we have different parameters where we have P1 is going to be 100 psi. T1 is 400 degrees Fahrenheit. Velocity 1 is 200 feet per second, and it leaves at a pressure, or it goes into a pressure, right? So we're having a nozzle that's coming like this right here, where we have this coming in and that going out. So this is 1 and this is 2, and so the P2 is 20.8 psia, and the V2 is 2,000 feet per second. So determine the final temperature. Find T2, and if the final state is a mix, find the quality. And spoiler alert, it is, but it's not much of a mix. It's pretty close to being saturated vapor. So as we mentioned in the previous one, we have this situation here where if you balance out the energies, you don't have, we're going to say this is well insulated, so no Q. We're going to say that it's doesn't have any work passing. So what we end up having is that the combination of enthalpy, thermal stuff, and also here dynamic stuff of the kinetic energy, those two things have to be equal to each other. And they were using insert and enter and exit, so inlet and exit. So we could actually just replace those with onesies and twosies, right? So it doesn't matter. So we want to look up what this is. We're given this. We're going to find this, and based on that, we're going to be able to find this exit temperature. Right? So that's our strategy for this. So let's look him up. First, let's look him up one way, and then look him up another way. All right. So let me see. This was where I just did this a second ago. I don't want to write a comment. I want to throw you away. Throw you away. How come I did these individually? Oh, there you go, together. All right. So we're going to go to the English one, which is in F, and I believe it's like F7.2. There you go. And what we say, we started out with 100 psi. Here's 1 psi. There you go, 100 psi. So boom, and we said it was 400 degrees Fahrenheit. There you go. So here is our enthalpy. Don't make that a mistake and just go to that column. I don't know why. I'm really drawn to that column instead of that column. So here's our H. This is a table. I'm writing this down. F7.2. F.7.2. We said that H1 is going at P equals 100 kilopascals. And T1 is equal to 400 degrees Fahrenheit. H1 is 1,227.53 BTUs per pound mass. Ooh, gotta love them pound mass. I also have this website right here. So, internet people, if you want it, maybe I'll try to remember to put it into the link into the comments, but anyway, or into the description. It's irc.wisc, I don't know what wisc.edu/properties2/. All right, so it's the IRC fluid thing. We can go to water here, and go to English units and go to absolute temp pressure. And so what do we say? 100. And then, oh, in this case, we want temperature. And the temperature is going to be 400. Now calculate properties. And it's interesting to me that they're not exactly identical right there. So you'll see that they get 1,227.741. Right, so that might be that this thing is interpolating internally, like it's got a series of data itself, and they picked different values to be the hard numbers, and this is a softer number where they're doing some interpolation in between things. Just so you know, that's how the system works. But what's really good for this one is that they'll do the interpolation for you, and you'll see in a moment why it's so much easier to use. So back to here. We're going to stick with this right here because this is what I have on my page. The problem that we have here is that this is, once again, just like in the previous video, this is in BTUs per pound mass. This is going to be in feet squared per second squared. And so we need to do some unit manipulation. So I have to say, if I have feet squared per second squared, how do I turn it into turn into BTUs per pound mass? Well, BTUs, if we want to change to something out of BTUs, we want to use what's called I think this is the mechanical equivalent of heat. So we go 778, and I don't use the 0.17 in there because that's silly. Foot pounds force per BTU, right? So now we got rid of BTU. That's great. We also, though, because a pounds mass just stinks to high heaven, we would like to get rid of pounds mass. So we have a way to do that. And because on the denominator here, we're going to multiply the top by 32.2 pound mass, and the units here are pound mass foot per second squared pound force. I know it's stupid. It's a stupid thing. But if you look at this, pound mass goes away. Feet, no, we don't want that feet to go away, sorry. We want the pound force to go away. And we're left with this feet times feet divided by second squared. Right, so we have just turned, by multiplying something that's BTUs per pound mass by 778 and 32.2, you can transform that BTUs per pound mass into foot squared per second squared. So now we've seen that they are compatible with each other. I promise it's just as stupid as it sounds, but that's what's done. And sometimes people have there's a conversion factor that you'll see around where someone takes 778 and multiply by 32.2. It's like 25,052 or something like that. 778 worth keeping in your memory banks. Obviously 32.2. And if you ever get confused by this thing right here, all you need to do is F equals MA, and you go pound force is equal to pound mass times foot per second squared, right there, right? And you go, well, how do you do that? Well, okay, well, so you can see that we could divide that over onto that, say, and you can see that we just put in there that the G into the thing, right, somewhere. 32.2 times pound mass foot divided by pounds force and second squared. It's just don't even think about it. It's you just hit the accept button right in there, I think. So anyway, back onto here, we'll take our and you can do either way. We could either multiply this or divide the other way out onto the thing. We want, though, BTUs per pound mass. So let's go ahead and divide this right here by these two values, and we won't bother writing everything out. 1,227.53. I'm going to leave the units off the thing. We've established that's how we're gonna do the thing. We're gonna do the thing. So VI is 200 divided by 778 and 32.2 equal to H exit plus 1/2 and 2,000. So this can be a larger number. But let's actually look at the in-between numbers. I don't think I did that. Good to look at the in-between numbers at things and see what is the influence of this. Even though that seems like a really lot, a whole lot. Let's see what this is right here. And I think I'm getting a text from my wife. I don't know what she's texting. She had a dinner program, so I could do it all I want. 32.2 divide. All right. So this is a very small number. 0.7984. Compared to that, I think it hardly matters at all. We could just ignore it. 2,000 divided by 2, divided by 778, and divided by 32.2. Right there. This is like 79.84. Still, that's more substantial than that, but that's not a whole lot. What we end up finding is the exit enthalpy is 1,148.5 BTUs per pound mass. And the problem told us the exit was P2 at 20.8 pounds per square foot. So let's try to use the tables, but spoiler alert, it's going to be a lot easier with the words. That's right, with the words. Well, use your words, Teddy. Don't call me Teddy. With the computer, with the website. Can't talk. All right, so we're trying to find maybe 20.8 in here, and oh, look at that! What a nice thing they did for us. 20.8 is the pressure right there. We don't have the pressure indexed tables in this version of the book, which is kind of a pain. But they were nice enough to at least pick this out right here. So we could go and find, this is the enthalpy, entropy. This is enthalpy. Right there. We can, I think it's my band. I bet it's my band, I blocked my band from buzzing me because they buzz too much. They talk to each other during the day. We can find, this is a table, F.7.1 at T equals 230 degrees Fahrenheit. Is that true? Sure it is, Fahrenheit. And P equal to 20.78 psia, so close to what we're doing. We'll have HF equal to 198.31 BTUs per pound mass, and HFG. Well, okay. Well, one thing we want to look at HF right here. HF is 1,157, and we had 1,000. No, what do we do? Yeah, we had 1,148.5. Right, so it's not hard to say that, oh, it's right in between these two, but really close to this one. So we know that we're going to be very much more a gas than we are a fluid. So I'm just going to only write down the 958.81 that I need to be able to find the quality. And so we could write for H is equal to HF plus X times HFG. We can write in 1,148.5 equals 198.31 plus X times 958.81, and we get an X equal to a boring 99.10%, right? So that's pretty much the identical problem that we had in the other one. But hold on for a second. Answers. We're going to have T2 is going to be 230 degrees Fahrenheit, and B, X2 is 99.1%. So here, hold on. Let's do the same problem, make our lives just a little bit easier, that we know that the exit was going to be 20.8. And here we had the enthalpy, right? So we can enter in what we decided the enthalpy must be, which is 1,148.5, and hit calculate properties. And sure enough, we could see that it says somewhere in here what kind of state it's in. And here's the quality right there. I don't know if you could read that. 99.1, right? 0.9911. So that was a lot easier right here. If you want to do that for homework, it's fine by me, but just cite that you did it, where you got it from, and but make sure you're able to do it during an exam, because you can't use this during an exam. So, end of lecture.